Need extra money for college? ISL Education Lending Scholarship Program provides $1,000 for college expenses. Registration is easy and no essay is required. Visit www.iowastudentloan.org/register to learn more. The scholarship is open to Iowa residents who are in high school and college students, as well as parents of those students. Register by November 30th for your chance at one of the 45 awards at www.iowastudentloan.org/register.
It's time to center mental health in Omaha. At Community Alliance, we're building a new center at 72nd and Mercy Road so that anyone seeking help for their mental health can access the personalized care they need to flourish. Support our campaign at mentalhealthomaha.org.
This is SpaceTime Series 23, Episode 68, for broadcast on the 6th of July, 2020. Coming up on SpaceTime: discovery of a cosmic ring of fire, the black hole that generated light, and a new name for an asteroid that's about to be slammed by a missile. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have captured an image of a super rare type of galaxy they're describing as a cosmic ring of fire. The galaxy, which has been named R5519, is located an incredible 11 billion light-years away, a time when the universe itself was still very young. R5519 has roughly the same mass as our own Milky Way galaxy. However, what makes it different is that it has a massive hole punched right through the centre of it, so it's ended up looking more like a giant cosmic donut. A report in the journal Nature Astronomy claims the hole in the centre is truly massive, with a diameter more than 2 billion times larger than the distance between the Earth and the Sun. And the galaxy is really active, producing stars at a rate 50 times greater than the Milky Way, with most of this activity taking place in the ring structure, hence the Ring of Fire description. One of the study's authors, Professor Ken Freeman from the Australian National University, says the discovery has implications for science's understanding of how galaxies like the Milky Way formed. Freeman and colleagues use spectroscopic data gathered by the giant 10-metre Keck Observatory up on Mauna Kea in Hawaii, together with images recorded by NASA's Hubble Space Telescope, to identify and study the unusual structure. The evidence suggests it's a type known as a collisional ring galaxy, making it one of the first ever located in the early universe. As far as science knows, there are two types of ring galaxies. The more common type forms because of internal processes, but collisional ones, as the name suggests, are the result of an immense and violent encounter with another galaxy. In the nearby local universe, collisional galaxies are about 1,000 times rarer than internally created ones. Images of the much more distant R5519 stem from around 10.8 billion years ago, just 3 million years after the Big Bang itself. And that suggests that collisional ring galaxies have always been extremely uncommon. Studying R5519 will help scientists determine when spiral galaxies first began to develop. That's because the collisional formation of ring galaxies requires the thin disk of the galaxy, that's the bit where the spiral arms are, to already be present in the target galaxy before the collision occurs. And remember, it's this thin disk that's the defining component of all spiral galaxies. Before they assemble, galaxies are usually in a disorderly state, not yet recognizable as spirals. So, this ring galaxy is already showing science what spirals look like at a time when the thin disks were only just assembling. Now, by comparison, the thin disk of our own galaxy, the Milky Way, is believed to have only come together around 9 billion years ago. Freeman says the discovery is an indication that disk assembly in spiral galaxies must have occurred over a more extended period of time than previously thought.
They're believed to be what you get when one galaxy basically falls almost directly through the center of another one. It doesn't have to be absolutely dead center, but depending on how off-center it is, depends on the kind of effects you get.
I immediately thought of Hoag's object.
Yes, exactly. Look, it probably is a Hoag's object. I'm interested that you've met that one. Yeah, it's probably that kind of object. I mean, that's what we think. Now, of course, those things look different depending on exactly how you are viewing them. We think Hoag's object, and there's a number of these known, not a very big number, there's a number of them known nearby. That's the kind of thing that we think they are. Now, of course, when you're out at the redshift of 2, that's a hell of a long way out, and you don't get quite the detail that you get with something like that's much closer, like Hoag's object and all the other ones. But it really does appear to be the same sort of thing, because it's a very well-defined ring, and they're pretty hard to come by unless you do something like that.
But 11 billion years ago, what does that say about galactic formation at that time? Because Hoag's object's pretty advanced.
Yeah, I mean, that's the thing that got me interested in it, I must say, exactly that aspect. I mean, you will get galaxies encountering all sorts of times. I mean, there's plenty of time, 11 between the Big Bang and 11 years ago for galaxies to have encounters, but you won't get that sort of result unless the galaxy has evolved perhaps a bit further than we would have thought galaxies would have evolved. I mean, the issue there is really that you don't get the neat ring unless the galaxy that's being hit has actually got a fairly well-settled disk. I mean, if it's just a turbulent ball and you run another one through it, you won't get a nice neat ring structure. I mean, you just get a slightly different turbulent ball. But if the galaxy's really settled down into a disk, now a disk usually means that things rotating, and most of the objects, gas or stars, are actually going around in circles, and it takes a little while to settle into that state, because the galaxies, as far as we can tell from observations, they start out pretty turbulent, and exactly where that turbulence comes from people argue about, but they are pretty turbulent, and that turbulence has got to take a while to
settle down.
Just basically settle down. It dissipates the big word. It's basically a settling down process. And if you hit it before it's settled down, as I say, you won't get a neat ring. And this is a pretty neat ring. It's perhaps not quite Hoag's object quality, but it is a pretty neat ring. So it means that they have got down to that point. Now, in our galaxy, we're sort of looking backwards, the settling process. So we look at stars of different ages in our galaxy, and we say, well, have they settled down or have they not? And you can go back maybe 9 billion years, and then after that, and the stars have settled down pretty well into near circular orbits, not perfectly circular orbits. But if you go back further than about 9 gigayears in our galaxy, you can see the remains of this turbulence that we see now if we look directly at galaxies at redshift of 2, 11 gigayears ago. So in our galaxy, it looks like the things hadn't really settled until somewhere around 9 gigayears. People argue about the exact number, but it's close to 9. Whereas here we're really going back another couple of gigayears, and it's a bit surprising. But very interesting that has happened, and that's, as I say, that's really what got me intrigued with getting involved in this project.
Back in those days, things would have been closer together, so you would have expected far more, just gravitational turbulence from other things nearby.
Well, that's correct, and mostly when we look at galaxies that are at that sort of redshift, which is at that sort of age, they are pretty turbulent.
Train wrecks are what we're often told.
I wouldn't actually call them train wrecks, but they're in the process. I mean, what I think is happening, not everybody would agree, but what I think is happening there is that you've got all these galaxies are basically a big lump of dark matter and a little bit of visible material, and it might be 10%, 5% of visible material. So underlying these galaxies is this big, more or less spherical thing of dark matter, which has kind of come to us from not much after Big Bang time. These things have just gradually grown. And somewhere around a redshift of 2, the big galaxies, they formed big dark matter halos, and they're starting to acquire the gas, and mainly the gas that is going to give you the star formation. And in that process of the material, the gas falling into the dark matter gravity, just the fact that it's coming in with a certain amount of energy gives it that energy is going to get turned into turbulence as it tries to settle down into the galaxy. And that, I think, is the source of a lot of this turbulence. It's just gas falling from the nearby universe into these dark matter
taking time to settle down then.
That's right, and it's that what I think causes most of the turbulence, particularly in galaxies that are going to be fairly neat rotating ring, disk type system. So it's a time when a lot of gas is coming into galaxies, and therefore you're getting a lot of star formation, and you see that directly. I mean, you take spectra of these galaxies at this sort of time.
It's described as being a ring of fire, which I'm assuming means that there's a lot of starbursts going on around the edges.
Exactly. That's right. exactly that. But most of the galaxies at that time are in a sort of starburst state. But it's just a bit surprising that while they're in that starburst state, they can be so, they can have such a neat disk that you're going to get a ring out of it all. I would have thought before we had this object that wouldn't actually happen, that you get encounters, but the things, they're bubbling away at something like 100 kilometres a second, which is a decent sort of velocity for inside a galaxy. It's far more than you would expect something that is trying to make a disk to have. And that was really the surprise with this guy.
Is it isotropic?
Look, you don't know. Probably it is, because gases tends to isotropy. I mean, you can have, it depends if you mean by the same.
Does the star formation rate appear to be the same all around the ring, I guess I'm asking? Can you tell at that distance?
To first order, yes. The answer would be yes.
That makes me think of a shockwave.
Well, this is sort of what it is. I mean, when you get the one galaxy falling through the other one, it's going to fall. It'll fall fairly fast, and it acts like a gravitational shock. So as it zips through the center of the galaxy, it pulls if this was a disk, it pulls the disk inwards, and then the encountering object goes away pretty quickly. Yeah. So as it goes through, it pulls the disk inwards, and then suddenly it's gone away. So that gravity's gone, and then the disk reacts by expanding at quite a rate, and that can certainly enhance star formation. Now, most of those galaxies at that age are really forming stars like mad anyway. So you might well have an original amount of star formation, and then you enhance that by giving it this gravitational shock. But it really is a shock. It's a very abrupt, discontinuous, we call it impulsive process. Yeah. So, no, that's absolutely right.
When you see something like that, do you ever wonder what it must look like now, 11 billion years later?
They'll be gone. The Hoag-type object, and there's the other family of these, they've all got fancy names, Cartwheel and stuff like that. They aren't going to last. The times involved in the contraction after the encountering one goes through, and then the subsequent expansion, they're like 1 or 2 billion years, and they'll settle down into something else. The ring usually, as far as we can see, it sort of expands, and then mostly I think it'll fall back in again. Now, it really just depends on exactly how much energy the encountering galaxy imparted, but I think for the most part, the people have done computer simulations of these, and for the most part, it goes out a certain way with the energy it's acquired. Gravity pulls it to a stop, and then it just falls back in again. And when it falls back in again, that's not a big deal. It'll just bounce once or twice and then just kind of settle down, and it could well finish up as a pretty ordinary-looking galaxy. Yeah, so these aren't long-lived things, but they're long-lived in the few billion year sense, but not in the Hubble time sense, the 13.8 sense. Yeah, no, they'll be well and truly gone.
We're learning more and more about galaxy evolution every day.
Oh, well, we do. And it's sometimes these oddballs that give you the surprises. Now, they're obviously pretty rare. There's been an awful lot of galaxies looked at that sort of redshift. There's been lots and lots of big surveys, big telescopes like Keck and Hubble, and as far as we know, that's the only one that's turned up. So it's an unusual situation. So it may just be that this galaxy had just gone a bit further with its evolution for whatever reason than most galaxies at that sort of redshift. I mean, redshift is basically equivalent to age, because we're looking back to the 11 giga years. So
you guys were using Keck and Hubble. James Webb will be looking primarily in near and mid-infrared.
That's right.
Would you like to see it in those wavelengths? See what else is there?
Yeah. I mean, see, you can do quite a lot from the ground in the infrared, and most of what we know, what I was saying about the turbulence, so that we know from infrared spectroscopy that's done from the ground. That's got all the usual disadvantages. I mean, working from the ground is a pain. The main pain is that there's so much other radiation around, and you're trying to measure these galaxies.
That's Professor Ken Freeman from the Australian National University. And this is SpaceTime. I'm Stuart Gary. Still to come, the black hole which generated light, and a new name for an asteroid that's about to become the target of a missile attack. All that and more coming up on SpaceTime.
See care in a new light at Madonna Rehabilitation Hospitals, where top medical minds lift you up, where the very best in specialized rehabilitation brings out your very best, where over 60 years of breakthroughs in research and technology spark your newfound strength. In our world-class hospitals, this is something greater than rehabilitation. It's renewed strength for life. Learn more at madonnarehab.org.
Okay, let's take a break from our show for a word from our sponsor, ExpressVPN, rated number 1 by TechRadar. You may be wondering why you need a virtual private network. Well, it's in the name. It's all about privacy. Do you really want big brother tech companies, hackers, governments, and who knows who else snooping in on your online activities? Now, you might not have anything to hide, but it's still really creepy, and it could be dangerous for you and those you care about. Also, how often do you run across a website and you want to get information from it, but you find out that they're geo-blocked? It's all very frustrating, and it's becoming an increasing problem. And that's where ExpressVPN can help you. ExpressVPN's a simple and efficient way to protect your online privacy. It's internet without borders from the world's leading VPN provider. So, protect your online privacy today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more. And of course, you'll find the link details in the show notes and on our website. That's tryexpressvpn.com/space. And now, it's back to our show.
You're listening to SpaceTime with Stuart Gary.
Astronomers have for the first time detected light coming from the merging of a pair of black holes. The spectacular flare reported in the journal Physical Review Letters could provide scientists with new details about the complex physics generated during these events. When two black holes spiral around each other and ultimately collide and merge, they send out ripples through the fabric of space-time called gravitational waves. And these are picked up by laser interferometer gravitational wave observatories like LIGO and Virgo. Thanks to this gravitational data, we now know that black hole mergers aren't rare, but actually seeing them is. That's because the escape velocity of anything caught too close to the black hole's gravitational well would exceed the speed of light. And since nothing can travel faster than the speed of light, nothing, not even light, can escape a black hole. However, every black hole has a broader region around it known as an event horizon. This is sort of a point of no return, and only when you pass beyond the event horizon, escape velocity exceeds light speed, and any matter or energy beyond this point will fall forever towards the singularity. So as long as you don't cross this border region, any light generated can still be seen. That's because you're not actually seeing the black hole itself, rather you're seeing the effect it's having on the matter and space around it. And astronomers believe that's exactly what's happened with this pair of merging black holes, which has generated light. The black hole merge has been catalogued as S190521G and was first detected by the LIGO and Virgo detectors on the 21st of May 2019 through their gravitational wave signatures. But later, astronomers using Caltech's Vicky transient facility at the Palomar Observatory near San Diego observed a sudden flare of light coming from the same location as the coalescing black holes. Zwicky undertakes robotic surveys of the night sky, looking for sudden unexpected events, such as visible signatures of gamma-ray bursts, fast radio bursts, novae, and supernovae. And it just happened to pick up a sudden flare generated in the accretion disk of material around an actively feeding supermassive black hole known as J1249 plus 3449, which just happened to match the time and location of the black hole merger gravitational wave signature. One of the study's authors, Matthew Graham from Caltech, says the supermassive black hole has been burbling away for years before this sudden flare erupted. Graham and colleagues suggest that the flare was generated because the two merging stellar mass black holes, which produce the gravitational waves, were orbiting within the accretion disk around a much larger supermassive black hole. Most, if not all, galaxies contain a central supermassive black hole. The Milky Way has one, known as Sagittarius A star, some 4.3 million times the mass of our Sun, located in the centre of our galaxy, some 27,000 light-years away. Now, these monsters are surrounded by swirling clouds of gas and dust, as well as swarms of stars. And with stars comes their dead counterparts, the white dwarfs, the neutron stars and pulsars, and the stellar mass black holes. And if two of these stellar mass black holes merged in or near the accretion disk, the new, now larger black hole would experience a sudden kick, sending it off in a random direction, and that could plough through the accretion disk, triggering a visible bright flare. Now, such a flare is predicted to have begun weeks or days after the initial splash of gravitational waves produced during the merger. In this case, Zwicky didn't catch the light event right away, but instead it turned up in archival data months later. The authors found the flare began just days after the gravitational wave event, and then gradually faded over the following month. Graham and colleagues were able to rule out other possible causes for the observed flare, including supernovae marking the death of a star, or a tidal disruption event which occurs when a black hole consumes a star. Also, 15 years of data from Caltech's Catalina Real-Time Transient Survey allowed the authors to confirm that this flare was also unlikely to have originated from the usual sorts of rumblings of the supermassive black hole as it regularly fed from the surrounding accretion disk. Instead, the black hole's activity was all relatively normal until May 2019, when it then suddenly intensified. That's why they think it had to be the merger of the two stellar mass black holes. Events like this are important because they provide clues about the evolution of galaxies, as well as astrophysics and cosmology in some of the universe's most extreme conditions. This is SpaceTime. Still to come, a new name for an asteroid that's about to be hit by a missile, and the United States Space Force launches the most accurate GPS satellite ever placed in orbit. All that and more still to come on SpaceTime. The International Astronomical Union has approved an official name for a tiny asteroid moon set to become the first ever target of an asteroid deflection mission. The 160-metre wide moon, which is roughly the size of the Great Pyramid of Giza, has been formally named Dimorphos, and it orbits around the 780-metre wide near-Earth asteroid Didymos. In July 2021, just over a year from now in fact, NASA will launch the Double Asteroid Redirection Test, or DART mission. DART is designed to slam into Dimorphos, providing astronomers with data on how the impact affects the binary system. It'll be followed in 2024 by the European Space Agency's Hera spacecraft, which will study the impact site and measure any changes in orbit. Together, the DART and Hera missions will demonstrate deflection technology which could be used to protect the Earth from hazardous asteroids by knocking them off a collision course. Didymos was first detected by the University of Arizona's Spacewatch project in 1996. Its little moon was then discovered in 2003, and the system was named Didymos, meaning twin in Greek. While the larger body in the system as a whole has gone by the name Didymos since then, the smaller body has been referred to by numerous names, including the provisional designation S2003-658031 and the nicknames Didymos B and Didymoon. The decision to give it an official title will allow it to be more easily distinguished from its larger companion. By the way, Dimorphos, well, that's Greek for having two forms, in this case, before and after collision. At present, there are some 546,077 numbered minor planets, of which some 22,129 have official names. After its launch next year, DART is scheduled to reach Dimorphos in 2022, deliberately colliding with it and creating a kinetic impact intended to alter the tiny moon's trajectory. The DART impact will be recorded by the Italian space agency Lycia Cube, a small CubeSat to be deployed by DART a few days before the collision. ESA's Hera probe will be launched 2 years later and is scheduled to arrive at Dimorphos in 2027, where it'll perform close-up surveys in order to assess the effects of the DART impact on the tiny moon structure and its orbit. The longer-term effects will be studied by telescopes here on Earth and in space. The Hera mission will also deploy 2 CubeSats. The Juventus CubeSat will use a low-frequency radar to scan the internal structure of Dimorphos, the first such scan ever performed by a spacecraft. Meanwhile, details of the second CubeSat to be carried by Hera are still being worked out. The results of Hera's detailed investigation will then be compared with the observations recorded by DART before the collision, thereby providing important insights into the effects of the impact. This is SpaceTime. Still to come, the United States Space Force launches the most accurate GPS satellite ever placed in orbit. And later on the Science Report, a new study warns that 1 in 7 kids who develop Kawasaki-like COVID-19 syndrome go on to develop nerve and brain problems. All that and more still to come on SpaceTime. The United States Space Force has launched its newest and most accurate global positioning system navigation satellite. The new GPS-3 SV-03 spacecraft, named Columbus, was flown into orbit aboard a SpaceX Falcon 9 rocket from Space Launch Complex 40 at the Cape Canaveral Air Force Station in Florida. The launch had been delayed by 2 months due to the COVID-19 pandemic.
Falcon's in startup. FTS configured for flight.
We are in startup on the flight computers. We are also beginning to pressurize Stage 1 and Stage 2 for launch.
Mission directors, go for launch.
We've heard the final call-outs. Mission director, launch director are go for launch. All systems are go for launch of Falcon 9 with GPS-3 Space Vehicle number 3.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff. Go Falcon, go GPS.
Vehicle is pushing down range.
And now we're entering the throttle bucket. We're powering down the Merlin engines. The 9 Merlin 1D engines
Mach
going
1.
back to full power. And we are now supersonic.
Max Q.
Guidance engineer calls out max Q, the period of maximum dynamic pressure, or Q, on the vehicle. From this point forward, although we go faster and faster, the thinner atmosphere will put less loads on the airframe of the rocket. Coming up next is chill-in of the upper stage engine. We've got a good trajectory.
And back engine chill started.
We've begun the chill-in of the upper stage engine. Power on the Merlin 1D engines looks good. Avionics reports everything is nominal. Next major activity, shutdown of the 9 Merlin engines, separate the first and second stage, and ignite the second stage engine to carry GPS and the second stage into the first of 2 orbits today. This one will be the initial parking orbit.
And Miko.
Stage separation confirmed.
And we've confirmed ignition of the second stage engine after a good Stage 1, Stage 2 SEP.
Both vehicles are following nominal trajectories.
First stage continuing to coast to apogee. The second stage engine beginning the long burn to get it into the parking orbit.
Acquisition of signal, Maryland.
Coming up, fairing deploy.
Fairing separation confirmed.
The 2 halves of the Falcon 9 fairing separating, the pneumatic system unlatching the locks that hold it together, and then the pneumatic pushers separating the 2 halves. The grid fins, the large titanium castings that are mounted to the first stage, have deployed. They'll be used later as we come back into the atmosphere for precision guidance. The second stage engine continuing to burn. It's at full power. Everything's looking good with the trajectory. So at just past T plus 4 minutes into flight, everything is go on the flight of Falcon 9 with GPS-3 Space Vehicle number 3.
Following MECO and stage separation, Falcon 9's first stage returned to Earth. Landing on the drone ship, just read the instructions, which had been pre-positioned some 350 kilometers downrange in the North Atlantic Ocean.
We're currently in the first of 2 planned Merlin vacuum engine burns. Currently looking at the data, the second stage engine burn is nominal. The first stage, as it's performing that reorientation, the grid fins are deployed. Some thruster plumes there from the attitude control system that are getting it ready so that the 9 Merlin 1D engines are pointed towards the atmosphere as it re-enters into Earth's atmosphere. Second stage is continuing into its burn. We're expecting this burn
Both
to
vehicles
last
continue to follow nominal trajectories.
5 minutes and 15 seconds. And entry burn will actually begin on the first stage in just about a minute from now. And during the entry burn, we'll ignite 3 of the Merlin 1D engines on the first stage. That'll give us a chance to slow down the stage as it ends up re-entering the Earth's atmosphere and reduce the aerodynamic loads as it starts to bite into the thicker parts of the air around our planet.
Stage 1, entry burn has started.
There's successful ignition of the 3 Merlin 1D engines on the first stage. We're expecting this burn to last just about 30 seconds.
Stage 1, entry burn, shutdown.
Some bursts there, some successful shutdown of the engine and some attitude control bursts just to get that orientation right. Now, once we get into the thicker parts of the atmosphere where those grid fins have some aerodynamic control authority, they will do most of the guiding to take the first stage towards our drone ship. Coming up, we'll have 2 events happening about the same time. The first stage will ignite its single center Merlin 1D engine for landing burn. About the same time, the second stage will perform secondary engine cutoff.
Stage 2 has entered terminal guidance.
Or SECO number 1. And while those 2 things occur about 25 seconds later, the first stage will hopefully touch down on our drone ship. In between, they're deploying its landing legs.
Drone ship, AOS. Stage 1 landing burn is starting. Seco 1.
Successful confirmation of shutdown of the Merlin vacuum engine. The guidance engineer is evaluating the orbit of the second stage now.
Nominal parking orbit.
Nominal parking orbit.
Landing
That's exactly what we want to hear. Landing leg deployment looks like right down the center.
And
looks
stage
like
1
a
is
successful
landed.
landing.
Recovery operators move into
I see it for stage. Excellent.
The 3,880-kilogram Lockheed Martin-built GPS-3 SV-03 is the third of 10 GPS Block 3 spacecraft currently being built. For the military, it includes a newer, easy-to-use M-code signal with greater power and range, giving improved anti-jamming capabilities, as well as greater secure access for high-accuracy military GPS signals. There's also a new L1C civilian use signal, which is backwards compatible with the existing C and A signal used by current GPS users. This will also allow greater civilian interoperability with the European Galileo satellite navigation system. And it will be backed up by a new L2C civilian signal designed for use in case of localized interference, such as tall buildings and stuff, and to compensate for any ionospheric delay errors. The new satellites are also providing improved L5 civilian safety of life signal coverage, with higher transmission power, greater bandwidth, improved signal structure for enhanced performance, and longer spreading codes. The GPS constellation comprises 33 satellites in medium Earth orbits at altitudes of around 20,180 kilometres, with an accuracy ranging from 500 metres down to 30 centimetres. The mission also marked the 88th launch of a Falcon 9 rocket, which was first flown 10 years ago this very month. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns that 1 in 7 children who develop Kawasaki-like COVID-19 syndrome may go on to develop nerve and brain problems. The findings, reported in the Journal of the American Medical Association, investigated 27 kids with COVID-19-related pediatric multisystem inflammatory syndrome, that's the Kawasaki disease-like symptoms that can affect kids with the virus, and found 4 who were previously healthy had developed nerve and brain problems. All 4 required intensive care unit admission, that's despite not suffering from any respiratory problems, and they showed symptoms including potentially personality-changing brain damage, as well as headaches, muscle weakness, and reduced reflexes. A new study warns that koala populations will be extinct in New South Wales by 2050. Parliamentary report found at least 5,000 koalas died during the recent bushfires, and more than 80% of their habitat had been destroyed. Meanwhile, land clearing for development and growing suburban sprawl remains the biggest threat now facing the dwindling koala population. It also found some 800 koalas between Campbelltown and Wilton, Sydney's southwestern suburbs, were extremely vulnerable because of urban expansion and busy main roads. Parliamentary study reached 16 key findings and made 42 recommendations to try and save the highly endangered species. These include establishing a koala national park along the Georges River in Sydney's southwestern suburbs, stretching from Fig Tree Hill to Glenfield, and establishing another national park on the state's mid-north coast, including an area near Kempsey currently earmarked for extensions to a quarry. It also recommended closing down all logging in old-growth forests. Scientists have built the world's smallest motor. The tiny molecular motor is less than a nanometer wide. It's made up of a fixed triangular stator comprising 6 palladium and 6 gallium atoms and a movable symmetrical acetylene molecule rotor. A report in the Proceedings of the National Academy of Sciences claims the molecular motor opens up the way for energy harvesting at the atomic level and can be powered by both thermal and electrical energy. A single electron is enough to cause the rotor to rotate by 1/6 of a revolution. Higher the amount of energy supplied, the higher the frequency of movement. But there are problems because it can make the rotor move in random directions. A bit of good news for those who like the occasional nightcap. It seems a little drinky at the end of the day might not be a bad thing as you're getting older. A report in the Journal of the American Medical Association examined the drinking habits of 20,000 American adults. They found the mental status of those who drank low to moderate amounts of alcohol during middle age and old age were better than those who abstained from alcohol altogether. Mental status was measured by testing word recall and vocabulary and by measuring levels of cognitive decline. They found the optimum level of drinking for brain health was between 10 and 14 drinks per week. Exactly how alcohol might maintain brain health remains unclear, and it should be pointed out that this type of study cannot show that drinking actually caused better cognition. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.